Hello everyone. Today we're going to be reviewing for our statistics exam. So let's get started. So some key statistics terminology. The population standard deviation is known as sigma. The sample standard deviation is known as S, the Roman letter. The sample mean is known as X bar, using a Roman letter. The population mean is known as mu, using a Greek letter. The sample size is lowercase n, or sometimes capital N. The null hypothesis is H sub 0, also known as H naught. The alternative hypothesis is H sub A. And the coefficient of correlation is R squared. Notice that for the population, we often use Greek letters, while for the sample standard deviation, we often use Roman letters. In fact, that's always the case. We have our agenda today. So that is for the T, the one sample inference when population parameters are unknown. The t-test, two sample inference when population parameters are unknown. T, paired inference, a paired t-test, a special case of a two-sample. One-way analysis of variance, also known as ANOVA. Two-way analysis of variance, also known as two-way ANOVA. Correlation and linear regression, predicting y from x. Multiple regression, predicting y from several x. Proportions, analysis of counts for two states. And chi-squared, analysis of counts for multiple states. We'll be combining proportions and chi-squared in one go. So basically, here is a table for you all to know which test to use. So basically, for quantitative data, we need a confidence interval to estimate and range for mean. Z-test we use to compare mean to a claim for a hypothesis test, and we use a Z-test when we don't know the population standard deviation. We use a t-test when we use a Z-test when we know the population standard deviation, and we use the t-test when we don't know the population standard deviation. The ANOVA we use for more than 2 factors. We can also use for 2 factors, but we often use it for 2 plus factors, like 3 factors. We use chi-squared for an association between two variables that are categorical. We use correlation and regression for categorical data. So number 1, we'll be going to one sample inference when population parameters are unknown. So when can we use the t-test? Well, first, the population has to be normally distributed. Secondly, the sample has to be a random sample. And thirdly, the sample size. We'll be talking about the sample size of when we can use procedures. For n less than 15, we can use the T procedure if our data is normally distributed and there are no outliers or skew to the data. When the sample size is between 15 and 40, we can use T procedures except in the presence of outliers or very strong skewness. For n greater than 40, we can use T procedures even if our data is strongly skewed. But one caveat is that there must be no outliers. Key formulas to know. So basically, T is equal to the sample mean minus the population mean over the standard error. The standard deviation of the sample over the square root of the sample size is known as the standard error. We use the t-score for the hypothesis test. We use it when we're trying to prove or disprove the null hypothesis. Or alternatively, when we are trying to prove or disprove the alternative hypothesis. For the confidence interval, this is the confidence interval. The sample mean plus or minus the t-score times the standard error. And we use this when we want to know a number. When the problem asks us for a number, like an approximate range of values for which the mean can be. the degrees of freedom is equal to the sample size minus 1. And we use this with the t-table. So when do we accept or reject the null hypothesis? Well, when the p-value found from the t-table from the t-score is smaller than alpha, we reject the null hypothesis. So example, if the t-score is equal to 2.056 and the p-value is 0.047, that's the p-value that corresponds to a t-score of 2.056, and alpha is at 0.05 significance at 95% significance. We reject the null hypothesis since the p-value of 0.047 is less than the alpha of 0.05. So our data is significant. What to do if we don't see our degrees of freedom in the t-table? An example of this, if we have a degree of freedom of 101 and 95% confidence, that is at alpha is equal to 0.05. As we can see, we only have degree of freedom of 100. We use the closest value of degree of freedom to 101, which is 100. And then we see that the t-score is 1.984 and the two-tail probability value is 0.05. The one-tail probability is 0.025. The t-table only has positive values, so if you are given a negative t-score and asked to find p, we use the absolute value of the t-score. So when to use the t-test versus a z-test? Well, for a hypothesis test and a confidence interval, we those are the two different things. So when we know the population standard deviation, we can use the z-score. The z-score is equal to the sample mean minus the population mean over the population standard deviation over the square root of n. So the standard error in a z-test is the population standard deviation over the square root of this the sample size. And we also have a confidence interval for the z-score, which is the sample mean plus or minus the z-score times the standard error. When we don't know the population standard deviation, we use t-score. So t-score is equal to the population mean minus the sample mean minus the population mean over the sample standard deviation over the square root of the sample size. And confidence interval is defined similarly. Number 2, we'll be talking about two sample t-test when the population parameters are unknown. So the two samples must be independent of each other. That's one caveat. So some key formulas. We have that the t-score is equal to the data from the first sample minus the data from the second sample over the standard error. We have a modified standard error is the sample standard deviation of the first sample squared over the sample size of the first sample plus the standard deviation of the second sample squared over the population size of the second sample. And all that is over a square root, is under square root. The degree of freedom for two-sample t-test with two independent samples is the smaller of the population sizes minus 1 if the population sizes are not equal. So basically, and keep in mind that the total sample size is the sample size of the first sample plus the sample size of the second sample. The confidence interval is the mean of the first sample minus the mean of the second sample plus or minus the t-score times the standard error. For hypothesis testing, we have that the null hypothesis is when the mean of the populations of both groups are the same. The alternative hypothesis is when the mean of one population is less than, greater than, or not equal to the mean of the second population. So alternative ways to state these, mu1 minus mu2 is equal to 0, or mu1 minus mu2 is greater than, less than, or not equal to 0. So in words, is there enough evidence of a difference between the population means from the sample means? So when to accept or reject the null hypothesis. So when the p-value is smaller than a, we can, okay, when the p-value is smaller than a, we can reject the null hypothesis. So, and we also have to think about whether we used a one-tailed or a two-tailed test. So we use two-tailed test when, for instance, the null hypothesis is mu1 is equal to mu2. The alternative hypothesis is mu1 is not equal to mu2, because we simply want to show that there is a difference between the two sample means. So we'll be using two-tailed test because we want to know whenever there is a difference, like even if it's greater, even if it's less. That's why we have to include those two dark blue areas. For a one-tailed test, the null hypothesis is that mu1 is equal to mu2, and then the alternative hypothesis is either mu1 is greater than mu2, or alternatively mu1 is less than mu2. So either of those. We simply want to show that one sample mean is greater or less than the other. Or actually one population mean is greater or less than the other. So this is the graph corresponding to that. For the one on the left, if we want to show that one is less than the other. For a two-tailed, it would be if the area was shaded over here instead, and that will correspond to the second one. How to check for normality? So we can use a normal quantile plot, which appears like this. How closely do the points fit the line is our question. And the closer the points fit the line, the more our data is normal. Number 3, we'll be talking about paired inference, a special case of two sample t-test. So in this example, we have two non-independent samples. In this t-test, we have two non-independent samples, and we want to create pairs between them. The pairs can be age, sex, the same subject at two different times with two different measurements of the same subject, and many others. Some key formulas to keep in mind is that the t-score is equal to the sample difference minus the sample mean difference minus the population mean difference over the sample standard deviation difference over the square root of the sample size. So mu sub diff is default 0 when there is no difference at all. So the degrees of freedom is the number of pairs minus 1, and it's the number of matched pairs. And the confidence interval is given by x bar diff plus or minus the t-score times the standard error, which is s sub diff over the square root of the sample size. On an exam, be sure to use the diff subscript when doing a paired t-test. That's very important. So hypothesis testing for the paired sample t-test. The null hypothesis is that the population mean of the first population is equal to the population mean of the second population. The alternative hypothesis is that the mean of the first population is greater than, less than, or not equal to the mean of the second population. So number 4, we have one-way analysis of variance. So basically, this is also known as ANOVA. And this is for testing more than 2 means. This only lets us know if there is a difference between the means, but we cannot tell whether they are greater or not. Because for instance, if you have 3 means, it's kind of hard to tell whether one is greater than the other or one is smaller than the other, but we can tell if there is a difference between the 3 means and if that difference is significant. There are 3 main assumptions in one-way ANOVA. That is that all groups are simple random samples, all different populations are normal, and all population standard deviations are the same. How does ANOVA work? So basically, you can see there can be variation within groups and variation between the groups. We mathematically calculate and compare the variability attributable to the groups, in between the groups, and the error, which is within the groups, and the total variability. Here's an example. We have the group sum of squares, the error sum of squares, and the total sum of squares. Here's another example. So some key terminologies: SSG is the sum of square for groups, SSE is the sum of squares for error, and SST is the sum of squares total, the sum of all the variation. Some key terms: SS sum of squares, SSG between group sum of squares, SSE error sum of squares, SST total variation sum of squares, DFG degrees of freedom between groups, DFE degrees of freedom for error within groups, DFT total variation degrees of freedom, MSG mean square between groups, MSE mean square of error within groups, MST mean square of total variation, MSG SSG, which is SSG over DFG, which is between group sum of squares over the error sum of squares, MSE, which is SSE over DFE, which is error sum of squares over degrees of freedom of error within groups, and that is equal to the total standard deviation squared. And the SP is the standard deviation of the population. MST, which is mean square of total variation, is equal to SST over DFT. SST is equal to the total variation sum of squares, while DFT is equal to the total variation degrees of freedom. The F score is equal to MSG over MSE. MSG is the mean square between groups, and MSE is the mean square of error within groups. We used SPSS, the statistical package for the social sciences, to get this output. Here's the logo for SPSS. The output of SPSS for in ANOVA as follows below. We can see the between groups, the within groups, and the total sum of squares, the degrees of freedom corresponding to each one. Notice that the degrees of freedom for the between groups plus the degrees of freedom for the within groups add up to the total degrees of freedom, which is 20, because 18 plus 2 is equal to 20. The F score is 0.055, and the significance level, the P score, in other words, is 0.947. Within groups is also known as error. Just keep that in mind. So some key formulas for ANOVA, we have that the F score is equal to the MSG over MSE. MSG is the mean square between groups. MSE is the mean square of error within groups. MSG is equal to SSG over DFG. MSE is equal to SSE over DFE, and that is equal to the population standard deviation squared. DFG is equal to the degrees of freedom between the groups. DFE is equal to degrees of freedom of error within groups. And we also need the formula for the pooled standard deviation, which is different than the population standard deviation. The pooled standard deviation is equal to the first sample size minus 1 times the standard deviation of the first sample size squared plus the sample size of the second sample minus 1 over this times the standard deviation of the second sample squared. And we keep doing that for as many samples as we have, and that is divided by the sample sizes of all minus the number of samples there are. and all that is under a square root. This is basically like taking a weighted average, and then we notice that we multiply each of the sample standard deviations squared by the degrees of freedom of that sample, and divide it by the total number of samples minus the number of samples we took, like the total elements in of all the samples minus the number of samples we had. Hypotheses. First hypothesis, null hypothesis is that all population means are the same. So that is mu1 is equal to mu2 is equal to mu3. We can have more than 3. Alternative hypothesis is that not all population means are the same. Critical values of F distribution, as we see here. One-way analysis of variance. Before running ANOVA, carefully examine the data using graphical and numerical summaries. So we can do task 1, are the standard deviations the same? Is the largest standard deviation greater than 2 times the smallest? If so, we cannot apply ANOVA. So for example, in this problem, the largest standard deviation is 4.397903. The smallest is 2.474240. And 4.397903 greater than 2.2474240. Unfortunately, it's not, so we cannot apply ANOVA here. So task 2, we want to do a means plot. So here's a means plot. These are sample data. For the samples, we can see that one of these groups, the MECL2 group, has a higher mean than the other. Does this hold up at the population level? We want to do a hypothesis test. So we can also have check by side box plots, as you see over here with an ANOVA with 3 samples. We see some worrisome things in this box plot. We have a pretty high outlier, and the data is skewed, as we can see where the mean lies for these 2 ones, and for even this one. What is R squared? That is known as well, SSG is between group sum of squares. SSE is the error of sum of squares. SST is the total variation sum of squares. R squared is equal to SSG over SST, and it's called the coefficient of correlation. It marks the amount of variability accounted for by differences between groups. So the null hypothesis is that all population means are the same. So mu1 is equal to mu2 is equal to mu3. We can have more than 3 population means, just keep that in mind. The alternative hypothesis is that not all population means are the same. So we have our F score of 0.055, our significance level of 0.947. We test that alpha is equal to 0.01. So the conclusion is that since the p-value is equal to 0.947, which is greater than alpha, we reject the null hypothesis because we have evidence that the population means are therefore different. Now what? We can use a multiple comparison test. We have 2 types. We have a Bonferroni, named after an Italian mathematician, and we have a Tukey. We use Bonferroni if and only if we reject the null hypothesis. We have to, in other words, show that there is a difference between at least 2 means before we use the Bonferroni. We use the Bonferroni if there is at least 1 mean that is different. So the Bonferroni multiple comparison test, here's just an example. Here's another example. So we can use the confidence interval also as a hypothesis test, which is kind of rare. We can only do this if our for two-tailed analyses. But ANOVA is always two-tailed because we can only show there is a difference. We use a two-tailed test only when we want to show that there is a difference, not necessarily that one is greater than or less than the other. So ANOVA is naturally always two-tailed because we can only show that there is a difference. So the confidence interval is if you subtract one from another and 0 is in the confidence interval, 0 is a possibility. So that means that they aren't different enough and the difference is not significant. As you see here, yeah, we can use confidence interval here because ANOVA is naturally two-tailed and we can only conclude a difference. Number 5, two-way analysis of variance. This deals with two factors instead of one factor. For instance, ANOVA for two factors tested simultaneously examples. We can have water and fertilizer. We can have gender and studying style. Some advantages of two-way analysis of ANOVA is efficiency, blocking. Blocking is like we can remove something from the overall effect. We can, for example, if we're studying learning styles, who learned better, we can take away male versus female to separate out variability. We can also test for interaction. So understanding two-way ANOVA. Variability is equal to the sum of the components, as we see here. In this example, in this specific example, there was no interaction because we ran out of degrees of freedom. Example 2 is with concrete. The response okay, so I'll first read this problem out. The strength of concrete depends upon the mixture used. An experiment compares 6 different mixtures. 9 specimens are poured from each mixture. 3 are subjected to no freeze-thaw cycles. 3 to 100 cycles and 3 to 500 cycles. The strength of each specimen is then measured. The response variable is the strength. The factor A is our first factor is the mixture. Our levels or values of that factor A is type 1, type 2, type 3, type 4, type 5, and type 6. So type 1 to type 6. Our second factor are the freeze-thaw cycles. And our levels of that is 0, 100, and 500. So our number of observations is thus equal to 54, and we got that from multiplying 6 by 9, 6 times 9. Because our experiment compares 6 different mixtures, 9 are subjected to no freeze-thaw cycles. 9 specimens are poured from each mixture. So the total population size is 9 times 6. Because within each of those 9 specimens, 3 are subjected to no freeze-thaw cycles, 3 to 100 cycles, and 3 to 500 cycles. Okay, so two-way analysis of variance, precision drilling example. So our conclusion for the tool, as we look over here, this is how we read the table. Our tool, the significance is very high because it's essentially 0. So we reject null. Conclusion for the time, again, we have a very small significant, we have a very small p-value, so we reject the null again. For the interaction between tool and time, we also reject the null because the p-value is very small. It's close to 0. So conclusion for the interaction, we reject null because we have one tool that is different from the others. So two-way analysis of variance, two-way ANOVA. Here's an example of what our hypothesis test might look like. Here we were testing sleep quality and gender. Those were our 2 factors. And are basically we have two hypothesis steps over here. One we're testing where is the mean between sleep qualities the same, and the second one are the means between the genders different or the same. The third one is if there is an interaction between those two factors, between gender and sleep quality. Number 6, we'll be going through correlation and linear regression, predicting y from x. So some equations that we have to remember are these ones. So the type of line, least squares regression equation of the line. So in a sample, we use y hat is equal to b sub 0 plus b1x. So the slope is b1. The y-intercept is b0. For the population model, we use a Greek letter beta 0 plus beta 1 x sub I plus Euler's Greek letter sub I. The slope is beta 1. The y-intercept is beta 0. The x is the explanatory variable, and the y is the response variable. We have to use y hat for the sample for the response variable. As we see over here, this is what we will see in a correlation and linear regression output. Regression gives you all that correlation gives you, plus the equation for making predictions and the best fit line, which is the equation. Correlation only gives you one number. It's a measure of how two variables vary together, how those two variables covary. And correlation can have a value of -1, 0, and 1, or any range between those. So basically -1 to 1. Correlation is sometimes also known as association. Variance is a measure of how individual observations of one variable differ from the mean of all the observations. Here we have an example of corn and rain. Our question was, are corn production and rainfall independent in the population? We want to test this at a significance level of 0.001. Our null hypothesis is that rho is equal to 0. Our alternative hypothesis is that rho is greater than 0. So rho for a one-tailed is equal to 0.000 divided by 2, because we have to divide that by 2 because they give us the significance level at a two-tailed place, as you can see here. Yeah. But it's still 0, so we are good there. Number 7, we will be talking about multiple regression, predicting y from several x's. So the general procedure is to look at the variables individually, and then look at the variables in paired correlations, and then do a regression with all the explanatory variables, and then we interpret the results. Are all the regression coefficients significant? And then we reduce to the best model. We also will talk about residual and normal probability plots, and those are used to check the assumptions. So some equations, as you can see here, this is pretty similar to the regression of two variables, except this is a lot more complicated. We can have as many x variables as we want, but not all the variables are useful. As we see here, our sample model from linear regression versus multiple regression, we also still use the Greek letter beta for the population slope if we are using the population model. And then we have residuals, which is equal to the population response variable minus the sample response variable. So residuals for linear regression and multiple regression are the same, and the assumptions for linear regression and multiple regression are the same. The assumptions are linearity, independence, normality, and constant variance. We can remember this by L, I, and C. Some hypotheses. Testing the individual slopes. For each variable, the known alternative hypotheses are null hypotheses, beta 1 is equal to 0, and alternative hypothesis, beta 1 is not equal to 0. So basically the population slope. One by one, we will drop those variables whose slopes cannot be distinguished from 0 from the full regression. What is the best model? When you remove a variable, it's a good move if r squared increases or doesn't decrease much, that is less than or equal to 3%. And if s decreases or doesn't increase much, the f-test statistic increases, the p-value decreases, and all remaining beta I coefficients are significant. The strategy is to remove the least significant variables one at a time and decide whether we gained or lost power. So here's a gun death example. Which variables do not seem to be a contributing factor to the regression? Which one is farthest from significance and can be dropped? So porn use is one of those. Porn use is only 0.003. So we want to rerun the regression, dropping porn from the list. As we see here, that beta is very insignificant. Because the significance level is very high, the p-value is very high, which means that it's not significant. That's a very small slope and it's close to 0. So number 8, we'll be talking about chi-squared analysis of counts for multiple states. The association between categorical variables is the chi-squared. Categorical variables are those whose values take a non-numeric state, such as political party, color, gender, race, flavor, height if categorized, and weight if categorized. Some equations for chi-squared is that the degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1 in a data table. And then we have 3 sorts of distributions, marginal, conditional, or joint distribution, and it is necessary to be able to recognize each of these. So here in dolphin activity, for instance, this is a joint distribution. If we are looking at the intersection of 2 values, time of day and feeding. What proportion of dolphins feed in the evening? Is this a marginal, conditional, or joint distribution? This is a joint distribution. We look at the intersection of 2 values, the time of day and feeding. What proportion of dolphins are do so in the morning? Is this a marginal, conditional, or joint distribution? So here we have a conditional distribution because the condition is that we narrow down a focus to dolphins that are traveling. That is our condition. And we look at one row only. What proportion of dolphins are active in the evening? Is this a marginal, conditional, or joint distribution? This is a marginal distribution because those that are traveling in the evening, we look at the total that are traveling in the evening. So this is the end of my presentation to help you guys review for statistics. I hope it helped, and see you next time for more videos.